In this video, we're going to take a look at an example of average rate of change and instantaneous rate of change. So if we were to go on a field trip to a bungee jump from the bridge shown, which is 467 feet high, we need some important information to design our bungee cord. As an object is in free fall, it gathers speed as it falls. In this activity, we'll estimate average velocity and instantaneous velocity at different times in the free fall. So first thing we do is write a function that models our free fall using d of t is equal to negative 1/2 times the pull of gravity, t squared, plus the initial velocity times t, plus the initial height. We're using feet, so pull of gravity is a constant near the Earth at about 32 feet per second per second. The initial velocity of a bungee jump, since you're standing still at the top, is 0, and initial height is 467 feet above the ground. So the function that represents the distance we are from the ground or the river after t seconds is d of t is equal to negative 1/2 times 32 t squared plus 0t plus 467. Simplifying, we get a d of t negative 16 t squared plus 467. So the graph of the free fall function is shown below. Estimate using the graph how long it would take to hit the water. So using our graph, it looks like there's the top of our jump. It shows every half a second about how far we are from the ground. And we would have a distance of 0 at about 5.4 seconds. If we want to know our average velocity from start to finish, remember rate times time equals distance. So the average rate of change would be basically the slope between 2 points on the graph, our change in vertical distance over our change in horizontal distance. So if we represent our 2 points, the beginning of our jump, when at time 0, you're 467 feet, and at time 5.4, you're 0 feet, and find the slope between those 2 points, we get an average of negative 86.48 feet per second. So that's our average velocity. Think of that as a straight line drawn from the start to the finish. So the straight line estimates average. So given a function that's not linear, f of x, the average rate of change of the function from the x value x equals a to b, is defined as f of b minus f of a, these would be the y values or the outputs, divided by b minus a, which would be the inputs. So our average velocity is the total distance traveled, which was the difference in total feet, divided by time in seconds. So the table below contains values for the graph, seconds and feet from the river. We want to use the values in the table just to find average velocity at different times during the drop. So the first idea of average velocity is basically taking the slope between 2 points on a nonlinear function. So if we want to take a look at our average velocity from 0 to 3 seconds, we would take a look at the two coordinates at 0 and 3 seconds and find the slope in between. We end up with negative 48 feet per second, so that tells us we're traveling on average 48 feet per second downward, that's why it's negative, from 0 to 3 seconds. Then from 3 to 5.4 seconds, the second half of our trip, when we take the slope between 323, and the coordinate 5.40, we end up with negative 134.58 feet per second. So we're traveling a lot faster the second half of the trip on average than we were the first half. And that is because our objects pick up speed or velocity as they fall. So that's algebra, is average rate of change. What calculus will tell us is, what if I want to know how fast I was traveling at exactly 3 seconds? We can't find the slope of the line because it's a point with itself, and you'd end up with 0 over 0. So think of a line drawn, a tangent line drawn, right there at the coordinate 3, 323. Our goal is to find our instantaneous rate of change. So we need some more information. So we're going to explore instantaneous rate of change. To do that, we're going to write an equation that models the average rate of change between 3, d of 3, which is the coordinate 3, 323, and any other point on the function. So we're going to leave it in variable format, t, d of t, which is negative 16t squared plus 467. So if we find the average rate of change between the two, the change in distance over the change in time, we subtract our y-coordinates over subtracting x-coordinates, and we end up with a function negative 16t squared plus 144 over t minus 3. So this tells us the slope between the coordinate 3, 323, and any other value point on the graph. All we need is the value of t. And since we want to know our instantaneous at t equals 3, we're finding the limit as our t values approach 3. So how this works is, let's use technology. We're going to type our function into Desmos. I'm going to use the function notation f of x equals negative 16t squared plus 144 over x minus 3. And then I'm going to find the interval, the average velocity from 2 to 3 seconds, I substitute 2 in my average rate of change function, and I get negative 80. So that means in between 2 to 3 seconds, I'm traveling at negative 80 feet per second. Then 2.5 to 3, all I need to substitute is 2.5 in the function, and I get negative 88 feet per second. So keep choosing values closer and closer to 3, and you'll notice as you choose values closer and closer to 3, your y values approach. Let's see, at 2.99, we're at negative 95.84. We're getting closer to 96. At 3, it's undefined, so let's look at the other side of 3, points a little bit further away that are higher than 3. If we put in 3.01, 3.1, and 3.5, notice that this undefined looks like negative 96 would fit. So we're looking at the pattern just like we did with limits, the numerical pattern, to try to guess what we think goes there. So we get negative 96 feet per second at 3 seconds. So what we want to be able to do is we want to be able to find the derivative of a function. You're going to find that in the next video. And what we'll be able to find is an equation that we can substitute 3 in, and it will tell us whether negative 96 feet per second is correct or not. All right, next example. On homework, you'll have some examples like our bungee, and it says in exercises 3 through 6, use the method to calculate the slope of the tangent line to the curve of each of the given functions. Let q1, 2, 3, and 4 have the indicated x values. Sketch the curve and tangent lines. So we have the function y equals x squared, and that's graphed here. And the point is 2, 4. So at that point, 2, 4, I'm putting a dot and then drawing in the tangent line. We're trying to find the slope of the tangent line at that value 2, 4. So we make an average rate of change function. That's our change in y over the change in x. So we're going to take our 2 points, the point x, x squared, that's just the general format of the point, and the specific point given, 2, 4, and create a function. So we subtract the y, subtract the x, and we end up with an average rate of change function of x squared minus 4 over x minus 2. So we want to find the limit as x approaches 2 of this function. So if we want to do this numerically, you type x squared minus 4 over x minus 2 as a function in Desmos, let it equal these particular values, and notice what f of x, or the y values, approach. And they're approaching 4, so that tells us that the slope of our line, tangent line, is equal to 4.